Focus to review. 1.52. In 5 minutes, Alan. It's still 3:55. I just got live here. I'm adjusting my screen and the field of view. I'll be on in 5 minutes. Ellen, can you do me a favor? If you're still there, can you check if my link is unlisted and or private, please? Hey guys, anybody who's there, can you please check if my link is private? Thank you very much, Alan. Appreciate that. Okay. And the lighting is good. You guys can see it. 1 minute. Okay, we'll get started, everybody. I see some 11 of you are there. Good afternoon. Thank you for spending your Saturday with me, reviewing for Quiz 2, Learning Objectives 1.5 to 1.11 for AP Chemistry. I have kind of put these learning objectives in two buckets. Learning objectives 1.5 through 1.8 deal with electron configuration, experimental evidence for that electron configuration, and PES, photon emission spectroscopy. And then learning objectives 1.9 to 1.11 deal with periodic trends. Okay, so I will start by reviewing the concepts of learning objectives, and then I can answer the questions. Feel free to type your questions if you have any. So the first learning objective here says that students should be able to interpret experimental data to come up with model, or based upon experimental data, should be able to propose whether a given model is right or not. Let's get the difference between ionization energy and photon emission spectroscopy clear. So I have a picture here. And in this picture, I have tried to draw two atoms, multi-electron atoms. So there are nuclear protons. In each one, there will be 11 protons because there are 11 electrons. And I have numbered the electrons so you can see different electrons. When we talk ionization energy, we are talking about the energy required to remove outermost electron. And that energy is not going to be different than the binding energy that you want to find out through photon emission spectroscopy. But now consider a scenario that you've lost this electron. You knock this off while you were measuring ionization energy. Now what's going to happen is there are still going to be 11 protons, but now there are only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in there. So as you know, effective nuclear charge will increase and the attraction of electrons to nuclear protons will increase. So if you're trying to figure out now the ionization energy of this electron, it is not the same as it was before this. And there's no way to figure this ionization energy in this form using the technique of ionization energy. What photon emission spectroscopy does is, using this technique in an atomic form, you can figure out the binding energy of any electron that is present here. Could be electron 4, could be electron 8, could be electron 1, could be electron 11, as it was present in atom. So photon emission spectroscopy is a technique that lets you measure the attractive force that an electron experiences from the nuclear protons. So that is binding energy. And we measure it by hitting a sample of that substance with photons, and we measure the kinetic energy that the electron comes out with, and whatever was lost is calculated as the binding energy of that electron. And what you end up getting is a graph of PES. And photon emission spectroscopy graph on the x-axis has energy in kilojoules or megajoules, depending on how large the number is. And on the y-axis, the peak shows you the number of electron. And if you are going from lower to higher energy, then know that your highest binding energy electrons, which are your 1s electrons, will be farthest out. So this will be 1s because the higher is here. 2s will be a little bit lower, but the same height. 2p will be further lower, and if they are 6, then they'll be 3 times the height, right? And so on. There are 2 types of questions that you can be asked on photon emission spectroscopy. One is you can be asked to interpret the graph, and other could be you can be asked to draw the graph. If you are asked to interpret the graph, one thing to remember is check x-axis for which way energy is increasing. Because sometimes it is in increasing order, sometimes it's in decreasing order. So you need to make sure you're reading it right. Now, second type of questions are drawing the graph. So they may say an element or draw the graph for carbon. And then you'll need to know that it is 1s2, 2s2, 2p2, and then you will draw the graph accordingly. One thing to remember as you draw the graph for elements, PES graph, if you are, say, for example, asked to draw carbon and nitrogen. So when you draw carbon, you will draw it, and you don't have to label the energy axis with numbers, just lower or higher or increasing energy. So let's say now this time we draw it in decreasing energy. Decreasing energy means high is here and low is here. And I'm drawing carbon right now. So 1s2 will be here, 2s2, 2p2. Okay. Now, if I'm asked to draw nitrogen, I know nitrogen is in the same period as carbon, but has 1 more proton than carbon. It's got 7 protons. So the effective nuclear charge will be greater, more protons, same shielding electron. So what's going to happen? Every single peak will be shifted towards higher energy. So nitrogen will be 1s2, 2s2, 2p3, right? So 1s2 will be shifted a little bit to higher energy. So to the left in this case, 2s2, 2p3 will be a third larger than this. So I'm estimating it, so about here. First, ionization energy is always the same as the PES binding energy, Stephen. That is correct. All right, so far so good. Any questions on PES, differentiation between PES and ionization energy? And you can be asked questions on PES to confirm a model or to elaborate that model. So you should know. So binding energy, because if you think about that, is nuclear protons are binding the electrons. What is holding electrons in an atom are these, the attraction from the nuclear protons, so like binding it together. Otherwise, the electrons will fall apart. Remember, like charges repel. But the attraction between the proton and electron is greater. It kind of binds the electron in there. That's why it's called binding energy. Good, Dan? So the answer, Stephen, is you go, remember we talked about effective nuclear charge, and Stephen's question was, why did removing the 11th electron affect the inner electrons? So the way you are thinking is only in terms of electron-electron repulsion. Yes, if you remove the 11th electron between 10, the repulsion is lesser, but that's not the only thing that's happening there. There are very many other things happening. There are still 11 protons, and you lost the entire 8 shielding electrons because the shielding now became the outermost electron. So the effective nuclear charge in this case is 11 minus 2 9. Here, the effective nuclear charge was 11 minus 10, just 1. You have significantly increased the effective nuclear charge, which totally outweighs the effect of decreased electron-electron repulsion. Is that clear, Stephen? Yes, Stephen. Increased effective nuclear charge makes the rings. So we draw rings. In real life, Stephen, there are no rings. The electrons are kind of scattered in the space, and why we call them in different energy level is because they're moving with different energy. So yes, electrons do get pulled closer, even the higher energy electron, the ring that you say. Yes. Would losing an electron, Brandon, I'm reading your question. Would losing an electron from oxygen make the atomic radii smaller? Yes. So in oxygen, make the atomic, yes. Across the period, remember atomic radius decreases because of the same thing. You are removing, you're adding protons, you are not adding shielding electrons, so the protons are able to attract these added electrons more, which is called effective nuclear charge. So Brandon's question, yes, losing an electron from oxygen make the atomic radius smaller. That's correct. If oxygen loses an electron, it does change the ENC. So guys, the thing is, there is not only one thing that's acting in any scenario. You remove an electron, yes, you're reducing electron-electron repulsion, but you're also increasing effective nuclear charge. And in different scenarios, the different factors weigh in more. So I know where Brandon is asking is, I think he's probably talking about that exception between nitrogen and oxygen, because ionization energy wise, but atomic radius consistently decreases across the period for the same reason. Atomic radius does not have the exceptions of ionization energy that we talked about. Brandon, are you clear about that? Okay, so tell me why you're confused. If oxygen loses an electron, the 2p sublevel would still exist. Yes, it will, but with less electrons. But doesn't that not change the ENC? Let's calculate it, okay? So it may not change the ENC, but let's calculate it, okay? Let's not speculate. So I have my periodic table here. I'm ready. So nitrogen is 7 and 14. Oxygen is 8, 0, 16, right? So in nitrogen, you have 7 protons. In oxygen, you have 8 protons. And you have 2. And then 1, 2, 3, 4, 5. And here you have 2. And 1, 2, 3, 4, 5, 6. So what is the ZF here? Effective nuclear charge. 7 minus how many shielding electrons? 2. So 5, what is the effective nuclear charge here? 8 minus 2, 6. See, it is higher. It's not the same. Because effective nuclear charge is about shielding electrons. If you don't add shielding electrons, you're adding valence electrons between nitrogen and oxygen, not shielding, Brandon. Did it clarify? No, Brandon. An element can lose electrons, but protons don't change at all. Protons never change because protons determine the identity of a substance. So protons will remain the same even though you've lost electrons. So actually, it's no longer an atom if oxygen loses an electron, which is very unlikely because oxygen is very electronegative. It wants to gain electron and not lose electron. But hypothetically speaking, if oxygen was to lose an electron, it'll become a cation. It's not oxygen atom anymore. And that cation will have the same number of protons, but one less electron. Make sense? So there are only one shielding electron, Brandon. Which are the shielding electrons? Are they inner or the outer? All the inner electrons are called shielding electrons. And I think that's where the concept differences. Let me draw it out. So in this picture that you see, can you see these pictures clearly, Brandon? All of these are shielding electrons. There's this, all of these. Everything in first and second level, this is not shielding. In this case, only this and this are shielding. All of these are not shielding because you have nothing in this energy level. So these become outer electrons. They are not shielding. Yes, ENC answer for Stephen is ENC changes between oxygen and its cation. And that is not always the blanket statement. It may or may not change. Have we calculated? I am not sure. Let's calculate. Because I have a feeling it will not change until you lose all of the valence electrons. So let's do it. If oxygen was to make a cation, you'll still have 8 protons. Your shielding electrons will still be the same. So Stephen's question was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. If this is oxygen cation, this looks so ugly, guys. It never happens in real life. Its ENC will be exactly the same. It will not change till you change the valence because it is still 8 minus 2. Yes. So, Stephen, ENC for oxygen's cation and oxygen will not change. And there will not be a significant difference in the atomic radius unless you remove all of these electrons. Now it will have no shielding, so it will be 8 minus 0. And then that will become considerably smaller. Iris, to clarify, if oxygen loses an electron, the ENC does not change. So what are, Iris, to answer your specific question, when you talk about ENC of oxygen, what are you comparing it with? Here, when I talked about oxygen's ENC is higher, I was comparing it with nitrogen. So ENC by itself is just a number. But when you use it to predict the radius, there should be a comparison. What are you comparing it with? So in this example, I compared oxygen with nitrogen. And yes, oxygen's ENC was higher as compared to nitrogen. That is why oxygen's atomic radius is smaller. Oxygen versus its cation, no. The ENC between oxygen and oxygen's cation is not different. It is exactly the same. But oxygen does not make cation. It tends to gain electrons, not lose electrons. But if it were to, let's say, hypothetically, which I cannot say because it doesn't happen, Iris, in that case, yes, oxygen and its cations ENC will be exactly the same. And their atomic radii will not be much different. Except then the effect of one less electron will take over because now ENC is about the same. All right, guys. So I'm going to move on from there on to how do you predict a model based upon ionization energy data. So far, we did it based upon photon emission spectroscopy data. So if it is ionization energy data, you will get data somewhat like this. Guys, can you see the board all right? Is it big enough font for you to see? Can you confirm that, please? I can move it closer always. Is the, yes, okay. So for ionization energy data, they may give you ionization energies of different elements and ask you different kind of questions. One type of question could be, how many valence electrons are there based upon ionization energy data? Stephen wants it a little bit closer, so I am moving it a bit closer. I don't want to drop it. Okay. Good, Stephen? Okay. So you will see that at some places, as you analyze the data, for element X, this is 500, this is 1000, and the third jump is certainly very much higher, 15,000. Here it is 200 and 2000 and 5000. So we can safely say that there is a huge jump between second and third ionization energies here, and there's a huge jump between first and second ionization energies here. So you are really looking for the big jumps in ionization energy. And the big jump is indicating that you have removed all the valence electrons, and now you're getting to the core electron, because core electrons experience a much higher effective nuclear charge. So to remove them takes that much more energy. And that is the only data you can glean from something given like that. So I would say in this case, there are two valence electrons. They may give you a corresponding electron configuration, and in one case put two electrons in the outermost, in one case not put that, and ask which is the right electron configuration based upon this data. Here, if you go from 200 to 2000, there's a big jump, so you can say it has only one valence electrons. So oftentimes these kind of questions will have a data table and electron configuration to prove or approve or disapprove that data. Shravya and Stephen, can you confirm that you're okay with this Zoom? I can move it further closer, but then my field decreases. But if it is good, then I rather leave it here. Otherwise, I can move it further closer. So Shravya and Stephen had asked me to move the board closer. Is this close enough, guys? Okay, perfect. Thank you. Thanks, Shravya. No, Stephen, I am sure there is a way to convert ionization energy data and binding energy, but think about it this way. Once you have ionization energy, you've already changed the atoms' attractive and repulsive forces, because electrons are not where they were. So no. If they're asking you ionization energy question, then they'll give you ionization energy data. If they are giving you PES data, they'll ask you questions related to PES. So you will not be asked to convert from in between ionization energy and binding energy. So that is the first learning objectives, 1.5 through 1.8, about PES data and ionization energy data. How do you approve or disapprove electron configuration based upon that, and so on. Now, I would like to move on to the periodic trends, which is the second chunk of learning objectives. And guys, when we're talking ionization energy data, one more thing that I would like to say is, remember, if you are talking ionization energy of an atom compared to its cation, compared to its anion, an anion's ionic radius will always be larger than its atom, and the reason is electron-electron repulsion. And a cation's radius will always be smaller than its atom because of increased attraction or increased effective nuclear charge, whatever the case might be. So ionization energy for an anion is lower, and ionization energy for a cation is higher. Okay, so that is one thing to remember. And second thing to remember is first ionization energy value will always be lower than second ionization energy, which will always be lower than third ionization energy. Or rephrasing it, ionization energy increases with subsequent removal of electrons. And it's fairly easy to understand. If you think you're removing an electron from a neutral atom and making it into a cation, now from this cation, if you try and remove another electron, remember opposites attract. So if it already has a positive charge, it will hold on to its electron a little bit tighter, either because it has same proton and one less electron or increased effective nuclear charge. So always remember ionization energy increases as you go from one to the other. And now I'll take the periodic trends one by one. So let's start with atomic radius. Atomic radius decreases across a period and increases down a group and the reason of atomic radius decrease across a period is increase in effective nuclear charge or ZF. An effective nuclear charge can be calculated by number of protons minus number of shielding electrons. So if you recall, what's happening here is 4, 5, 6, 7, 8. And what's happening is if every time when you're adding electrons, you're adding in the valence shell. They all have 2 shielding electrons. I'm drawing the second period. And as you add 5, so they go here. And 6, now 4 go here. And 7, now 1, 2, 3, 4, 5 go here. And 8, 1, 2, 3, 4, 5, 6 go there. So across a period, you're not increasing shielding electrons. Shielding electrons are same, but number of protons are increasing. So now the protons can attract the electrons more with nothing coming in between them because we're not adding shielding electrons. Let me take Steven's question. I'm sorry, I didn't look at my screen. So I'm going to go back, guys, from here to the previous learning objective for a second. That is correct, Steven. Steven's question was, so the PES graph for a cation will have the peak shifted to higher binding energy? Yes, that is correct. Coming back, switching back to the atomic radius, going down a group, what's happening is you are adding, let's say 14, I don't remember which ones you are adding protons going down, but you're also adding energy levels going down. And with energy levels, atomic radius increases, but also you're adding electrons in those energy levels. As you're adding electrons, the electron-electron repulsion and increase of energy level causes an increase in atomic radius going down the group. So going down, the reasons are increase in energy level and increase in number of electrons, so more electron-electron repulsion. So that was atomic radius. Any questions about atomic radius? We're doing good on atomic radius, guys? Remember to use keywords. They are important. No problem, Stephen. Keep those questions coming. So now let's move on to ionization energy, which is our second trend. Ionization energy is the amount of energy required to remove the outermost electron in its gaseous state. It has to be in gaseous state. So an atom, you have to write that G. It has significance. And whatever energy is required to remove that first electron is called first ionization energy. It is generally in kilojoules per mole or kilojoules. And then if from here in gaseous state, you remove yet another electron, then that is called the second ionization energy. And second ionization energy value is always higher than the first ionization energy. Now, as we go across a period, remember, atomic radius decreases, down the group, atomic radius increases. So ionization energy trend is just the opposite of atomic radius, because it'll be easier to remove that electrons. Across a period, it's easier to remove the, across a period, ionization energy increases because atomic radius is decreasing. Effective nuclear charge is increasing, so it is harder to remove an electron. Going down a group as the atomic radius is increasing due to increased energy levels, it becomes easier to remove electrons because of lesser attraction by nuclear proton. So down a group, ionization energy decreases. And there are two exceptions to this trend, and I'm going to go over the exceptions, but before that, I want to take questions on ionization energy. Anything about ionization energy that you want me to clarify further? The gaseous part is important, Shravya, because what happens in our day-to-day life, most of the things you see around you are present as solids or present in bonded state. But before an electron can be removed from an atom, it has to be made into gaseous state because particles are moving faster. It becomes easier to remove electrons. So let's say if some atom existed as solid, you have to first convert it to gas, right? Gaseous state. And converting from gas to solid, solid to gas, as you know, requires energy, right? This energy is not counted as part of ionization energy because then we won't be able to compare, because there are different types of bondings and atoms and molecules are connected with each other with different amount of energy. So there is a whole, let's say the start line is here for measuring something for standardization, say somebody comes running from here and somebody comes running from here and somebody comes running from here. And if we were taking all of that to be one, how do you compare? You can't compare this part then, right? It is the overall part. So for standardization's sake, we have said once the atom is in gaseous state, now let's see how much energy is required to remove that electron, because that kind of standardizes things. Make sense, Shravya? Dan, ionization energy. In fact, there is a very nice video. I'm going to send you the link or remind me on Monday in class. So Berkeley actually has the whole equipment of ionization energy, and they show how they feed a sample, how they convert it to gas, and then how they knock off the electrons and how they measure it. So that's a conversation for another day, but there's a great video where you can see step by step everything's happening. And the machine looks nothing like more than like a tin box, a big tin box, but it does pretty fancy stuff. So I'll be happy to share that with you. Just remind me, okay? So from here, I'm going to go over the exceptions. I'm taking more questions. No, ionization energy, well, you can, yes. Yes, Iris, and no. Iris's question is, would ionization energy go here? You can write energy two types. Either you can write energy here, or you can write energy with a positive or negative sign. And we'll be talking about that in thermochem. So for now, when I write here, it is like positive 10 kilojoules per mole, or just 10. If you write it like that, it means the same thing as plus 10 kilojoules here. They both mean the same thing. We are writing it as delta H here and writing it as energy here. But for now, I don't think that's relevant. We'll deal with it when we come to thermochem. All right, Iris? You're welcome. Okay, so ideally, ionization energy should be increasing because radius is steadily decreasing across a period, right? But what happens if you look closely? This is group 1, this is group 2, and I haven't drawn bunch of the middle transition metals, okay? Then this is group 13, 14, 15, and so on, and 16. Might as well draw that while I'm here. Their ionization energy increases from here to here, then show a decrease between these two, and then increases here, and then shows a decrease, and then increases. So rather than the ionization energy trend being like this, which it should be steadily increasing from left to right, let me make a straight line. Steadily increasing, it goes up, then goes down, goes up, then goes down, then goes up. So what is the reason that the ionization energy shows a little decrease between 2 and 13 and a little decrease between 15 and 16? And I think, guys, on my keywords document, I wrote between 13 and 14. That was wrong. Between 15 and 16 is what we are talking about. So let's see individual reasons. Pay attention because the reasons remain the same for electron affinity as well. So here, when you're adding electrons, this is 1s1 or s1, it could be second group, s2, and this is s2p1. So here, when you are removing electron, you're removing electron that is moving in a spherical shape around the nucleus. So nuclear proton always have access to this electron and are attracting it. But when you go to p electrons, the s electrons are moving in a sphere, but the p electrons are moving in a dumbbell shaped. So probability dictates that a lot of times the electrons might be very far away from the nuclear protons. So nuclear protons are not able to attract the p electrons as strongly as they can the s electron. And that is why when you want to remove an electron from p sublevel, it shows a slight dip. Thanks, Iris, for answering that question for Brendan. Yes, it will be recorded and I'll put it on Facebook group so you guys can use it to review multiple times. All right, now what happens is the second dip here. So this is P1, this is S2P2, this is S2P3, and this is S2P4. If we draw orbital diagram, from here to here, one p electrons being added. But when we talk about P4, the fourth electron is being removed from a paired orbital. Orbital is a small 3D space around the nucleus, right? Where the electrons are moving. So when two electrons are in close proximity of each other, there is a certain repulsion between them. And because of this repulsive force, it's easier to remove this electron. So you see a slight dip in there. Are the exceptions clear? And this dip doesn't only happen in the first period, but happens all the way down in the periodic table between those two neighboring atoms. Any questions about the exceptions of ionization energy? No, Brandon, we are talking about removing electron. Ionization energy deals with the removing electron, not adding electrons. So here we are removing an electron from a paired p orbital. And because we are removing a paired electron, there is electron-electron repulsion. And that lessens the amount of energy required to remove it because there's already repulsion, a desire to push it away. Because ionization energy will increase. So ionization energy across, Brandon, is guided by one thing, which is decrease in atomic radius, right? That is one factor that's constant throughout. Now, in addition to that factor, that the atomic radius is decreasing and ionization energy is increasing, some places, some things happen that mean more than the decrease of atomic size. And one such place is between 15 and 16. So while between 13, 14, 15, what is determining the increase in ionization energy is the decrease in atomic radius. Between 15 and 16, that factor is overshadowed by the effect of electron-electron repulsion, because now you are removing electron from a paired orbital rather than an unpaired orbital. We are not talking adding, we are talking removing. Yeah? Okay. So between K and SR, Stephen's question, K and SR, if it is moving across one and down one, you will not be asked to answer those because they have better things to ask you. You will not be able to tell. That is Stephen's question. Brandon, you're welcome. Chelina's question. There is no such correlation, Chelina. I wish I could tell you that there's always such a correlation. Where you will always see a dip is this group. Between the 16th group will be lower than the 15th. And yes, 17th will be higher if that's what you're asking. Is that what you were asking? So 16th group elements will all have lower energy than the 15th group elements. But then 17th group elements will have higher than 16th. Will they have higher than 15th? Ideally, yes, but sometimes you can see that. Okay. Now let's get to Big Kahuna, electron affinity. Okay, so electron affinity, remember we talked about electron affinity, electronegativity, and ENC, effective nuclear charge. And I'd made a diagram to clarify the difference between three, and I would again do that. If you have an atom and there are nuclear protons in the middle, the force of attraction exerted by these proton on the outermost electron, this is called effective nuclear charge. So effective nuclear charge refers to how much attraction an atom's outermost electron feel from its own protons. Electron affinity refers to if you have an atom, it has its own electrons, let's say 2 and 1. Now another electron approaches it. How much attraction will this incoming electron feel from the nuclear proton? That's called electron affinity. And this, because the protons are attracting the electron, will depend or will be defined by Coulomb's law. And Coulomb's law says that the amount of energy released, electron affinity, will be proportional to the product of the charges and inversely proportional to the distance between them. So if you have two atoms, this is atom 1, and if you have this atom and an incoming electron here, the distance is r here, and the distance is r, you can see that atom number 2 will have lower electron affinity because of increased distance. Another thing is electron affinity is actually the amount of energy released. When an electron is added to a gaseous atom in its neutral state. So if you have an atom and you add an electron to it, it forms an anion, and whatever is the amount of energy released, that is called electron affinity. And the higher the negative value means force of attraction, negative value of energy. And the positive value of energy means repulsion. It doesn't really want it, but you're forcing it in there. So attraction and repulsion. So a higher negative electron affinity, 100 kilojoules versus 50 kilojoules, this is higher electron affinity versus 50, because the sign is just showing if the energy is released or absorbed. It's not a negative number. Electronegativity only applies to covalently bonded atoms that are sharing an electron pair. And between atom A and B who are sharing this pair, which of the atom will attract the electron pair more towards itself is called electronegativity. And you can see if there are two atoms like that, then the shared pair is going to be closer to the smaller atom. So generally, the smaller atoms have higher electronegativity. And electronegativity is not the actual energy, but it is a tendency which goes on a scale of 0 to 4. And remember, fluorine, it always gets 4.0, right? So as you go across a period now, I will come to electron affinity in a minute, electronegativity will increase. And indeed, fluorine is very high electronegativity element. Electron affinity, same trend, because the atomic radius decreases across the period. Electron affinity will also increase across a period, and electron affinity will decrease down the group. And just like ionization energy, there are two exceptions in the trends, which I will tell in a minute, but I will give you a few minutes to ask me questions on electron affinity. Any questions on electron affinity, anybody? I think you get it, huh? All right. Now I will do exceptions to electron affinity. So the trend dictates that as you go across the period, so let's say 1, 2, and there is like whole transition metals in between, 13, 14, 15, 16, 17, right? These are the group numbers and going down. So electron affinity going down decreases, no problem with that, as the atomic radius is increasing. But as it goes across, ideally, electron affinity should increase steadily. From here to here, it should increase. But again, what happens? That experimental results indicated that there is a drop So the electron affinity, whatever is there, it goes down between this and this, goes up again till here, and between 14 and 15, it drops again. And after this, it goes up again. So there are two distinct drops between group 1 and 2 and between group 14 and 15. And the reason for these drops is exactly the same as ionization energy, just their place is shifted one group before, because now you're talking about adding electrons and not removing electrons. So what's happening? This is 1s or S1, this is S2. In S1, if you are talking about adding electron, you are adding to S sublevel. But if you are talking about adding electron here, then you are talking about adding the electron to the P sublevel, this electron. And remember, P electrons do not penetrate the nuclear region the same way that the S electron can. So P electrons are not that attracted. So as an electron is trying to come in the P orbital, the nuclear protons cannot attract it as much. Hence, there is a slight dip in electron affinity between groups 1 and 2. Now, the second difference happens between groups 14 and 15. So this is S2P1, this is S2P2, S2P3, right? And S2P4. So what's happening here is, if you look only at P, you're adding, when you add that electron, you're adding to the P sublevel. But here, when you are adding the electron, the P is already half filled. So you're adding the electron to an already occupied sublevel or orbital, not sublevel, orbital. And due to electron-electron repulsion, it'll be harder to push this electron in here. And that is why you'll have to put energy to put that electron in there. It's naturally not desired. That's why there is a slight dip in electron affinity between groups 14 and 15. Any questions about electronegativity or electron affinity? I see there are a couple. So electronegativity will be explained with Coulomb's law, and electron affinity will also be explained by Coulomb's law. The only thing that really is explained by ENC is the atomic radius. Right, Chelina? No, you don't have to calculate a numerical value for electronegativity animation, but you should be able to conclude, if I say that electronegativity of this element is negative, blah, 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 and this one is negative, blah, 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 you should be able to tell which is a higher one. So they may want to sometimes test your knowledge of negative number versus negative as a direction of energy transfer. You're welcome, Chelina. So electron affinity is a tendency to add an electron to itself. So when an atom really wants to add an electron, the protons have a direct access to attract those electrons, right? So if there is already an electron and it is saying, no, 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 don't come, right? There's a repulsion. So then you will have to push it in Shravya. Think of it like you're living in your bedroom all happy by yourself, and your mom tries to pawn off your sibling in the room and you don't want it. So there's going to be resistance, right? It's not going to be very welcome move. That's the same thing with electrons, because each of the P sublevel, P orbital in P sublevel is occupied by electron. When you want to add another electron, so you have to think of orbital as a very small area of sublevel. And in a sublevel, electrons are farther apart, but within an orbital, electrons are closer together. So then there is that repulsion there. No. Iris asked if, is it possible to have a negative value of electronegativity? No. You have 0 to 4 is the range of electronegativity. Electron affinity is the one that has negative value. And it is not negative value. Remember, negative is the direction of energy transfer. In chemistry, when an atom really attracts an electron, it releases energy, and that's taken as negative. Shravya, that is correct. Electron affinity is the amount of energy released when an electron is added. You're welcome, Iris. So Shravya, coming back to you. It is the amount of energy released when an electron is added. Correct. And because it's energy release, it should have a negative sign. So the last bit is metallic character. And metallic character is ability to lose electron. And as you can see that it will be guided by the size of atom. The larger the atom, the easier it is to lose the electron. So your strongest metals will be bottom left of the periodic table, and your strongest non-metals will be top right of the periodic table due to the size. So 0 to 4 rating represents ability to attract shared pair of electron in a bonded situation. And these are experimental values, not a theoretically predicted thing. And they measure these values, and fluorine has the highest electronegativity. Dan, that will be correct statement. When electron affinity is positive, it means that the atom almost has no attraction for the electron. You have to almost force the electron to it. A low negative value will mean lower attraction, but still there's attraction. 0 means kind of neutral. Positive means you have to force the electron in. All right, guys. So today was the concepts podcast. I see one person liked it. And tomorrow will be the practice problems. And practice problems, I'm going to move that a little bit, guys. Oh, thank you for liking. I so appreciate it. Tomorrow, I'm going to move the practice problems to a little later time, guys. This kind of comes in the middle. I can't go work out or do anything. It's still the sunlight outside. So would it be okay, guys, if I did tomorrow's session, say 8:30 to 9:30? Or will that be too late to answer your practice problems? Can you just quickly tell me if 8:30 would work, or will it be too late? That works. I heard from Adria. Okay, how about anybody who thinks it doesn't work, type it, because default is it works. Thank you. Can we go 7:30? Shravya, 7:30, smack in the middle of dinner time, girl. You guys should be eating dinner with family, and so should I, right? So that's why I thought we can be fed and watered and then come and do some camp. Do you have a conflict? Could it be too close to bedtime? Oh, that's music to my ears, Alan. You do sleep by 9:30, don't you, buddy? At least I do. But yeah, my brain will still be active. I'm okay. But I can do maybe 8. I can do 8, no problem. I can do 8 to 9. How about that? Okay. I'll do 8 to 9 and I'll put it on the Facebook group, and you guys are all connected with your friends, so you can let them know it's going to be at 8. Okay, you got it, guys. I hear 8. So I got it. Perfect. I'll do at 8 tomorrow. And remember, you guys are so welcome. I appreciate you hanging out with me. And one thing that you want to take from this is, if at my age, I can put myself in uncomfortable situations and learn more, I hope you guys will be willing to do that, because life's bigger than chemistry. So learn. Thank you. And it's my joy. Thank you for connecting with me. And thank you for being you. And I will be back tomorrow. And remember, Facebook group is also a resource for you. So you can always put questions there. So then everybody kind of learns and grows with each other, okay? Otherwise, I'll see you 8 p.m. tomorrow, elements. I'm going to end the stream. Bye. Thank you, everybody.